Hello class, this is Ms. Jacoy. So this is page 26 and 27 in your momentum packet. So this is meant to be a bit of like a kind of an FRQ calculation practice for a slightly more complex momentum problem. So again, make sure you have already tried all of page 26, 27. Give yourself about 10 minutes. So make sure you do this. And then come back and correct it in colored pen. I actually will be grading you guys down if it's not in colored pen. So make sure you do that just so I can differentiate how much you were able to do and how much help you needed to finish solving it. Alright, so now that you have paused and tried it on your own, first thing for any problem to do is read over it. So we have an 8-gram bullet is fired at a 250-gram block that is initially at rest on the table, or at the edge of a table at a height of 1 meter. As shown in the picture above. The bullet remains in the block, and after the impact, the block lands 2 meters from the bottom of the table. So A. The bullet lost some momentum during the collision, while the block gained some momentum. Which is larger? Now hopefully, seeing that the block is on a table, this is why they specified edge. The idea behind writing at the edge of the table, it's not really going to experience that much friction, and really you're talking about just during the collision. So if it's just during the collision, they should be exactly the same. Because we have conservation momentum, so all of that momentum in our bullet before should be equal to the momentum of our bullet now, plus the momentum that our block has gained. Unfortunately, bullet and block start with B, so one is B and one's BL, but anyway. One's for the bullet, one's for the block. But overall, they should add up to whatever momentum the bullet had before. So however much the bullet slowed down and lost momentum, the block gained momentum. And now they move with whatever that momentum is together. That being said, they now want you to calculate the initial speed of the bullet. So that is definitely a multi-step problem. So again, if you have not, take a step, think, how could you solve this? I'll be right back. And if you're not sure where to start, this starts off as a kinematics problem. So just to give you a quick thing before I go all the way through it, to figure out how fast the bullet is going, we need to know what its momentum is after. And we do know some things about the after. We know that it goes 2 meters after having a chance to fall for 1 meter. So this is essentially 2D kinematics, finding the speed. And then once you have our new speed, we can then go back and figure out, well, if I have the speed of my new object, I can figure out the speed and mass of my old one. Alright, so first off, as I said, we need to figure out the speed, or the velocity, right here. So we need to figure out this velocity in the x direction, because this bullet does hit it in the x direction. But to do that, remember whenever you're finding a thing, we have to first find time. So we need to find time, then we're going to use that to find the velocity in the x direction, then we're going to use it to find the momentum at any given time. So remember, to find time, we're always going to use our y components. So things we know about in the y direction. So first of all, we know that it essentially has a change in position of 1 meter. It gets to fall 1 meter. Acceleration in the y direction is always 10 or negative 10, depending on how you look at it, your frame of reference. This is meters per second squared. You should write them. If I write them, it will be very messy and hard to read, so I'm not. But it should always be 10 meters per second squared, or 9.8 if you don't feel like rounding. Our initial velocities, since it's sitting flat on the table, are going to be 0, which is very nice for everyone involved. And then we are looking for time. So if we're looking for something that has x, acceleration, and only an initial velocity, we are definitely looking at our first equation. So we're going to take our first equation. We know that the change in x, I'll write the whole equation, x equals v naught t plus 1/2 at squared. We know that v naught is 0, so that whole term cancels to 0, which makes, again, our lives much better. That's just 1 meter. Then we have our 1/2 AT squared. I just decided not to put in the variables for a second. And then you're going to move your 2 over, so it's going to be 2 divided by A equals T squared. And then if we square root that on both sides, we're going to get this. I just didn't put the number in because I didn't feel like putting the number in, to be honest. Alright, so once we're here, we now put it into the x side of the equations. Make sure you are writing down and pausing because I'm going to have to start erasing stuff to just have room. So here we know that our delta x is 2 because it went 2 meters in the x direction. Our v, our initial v is what we don't know but definitely want to find. And then remember, acceleration in the x direction, unless it's like strapped to a rocket, after that collision is over, there are no forces acting in the x direction, which means we have no acceleration in the x direction. So that's going to be a 0, which again makes our life better. So we're going to have this is delta x in the x, this was in the y, just to be clear. So I could write out the 1/2 AT squared, and I will just to show you, but that's not going to be anything because our acceleration is 0. So the only thing affecting this is just the velocity. So it has a constant velocity here. So you know this is going to be 2 divided by whatever our time is, divided by our time into v naught. Alright, so from here you can start plugging in some numbers because you're just going to take this once you plug in for your A, and of course your acceleration in the y direction is just going to be gravity, right? So you can plug in for that, and then once you find this t, you plug in for here, you find your initial velocity. Something to note, that this is not the initial velocity of the bullet, this is the initial velocity of both the bullet and the block as they go off that ramp. So you're finding this velocity up here, right? So as they go off, and then once you get there, then you can use conservation of momentum. So let's get there first. Let's plug in your numbers, and I'm just going to pop out the numbers. I don't want to plug in numbers on this. Alright, so plugging all those numbers, I got my velocity to be about 4.47. I did use 10 for the acceleration, so if you use 9.8, it should be a little different, but not too different. If it's very different, check your math, check mine. I may have just plugged things in wrong. It happens to the best of us. Alright, so I'm going to erase all of this work. We're going to keep this number as essentially our exit velocity right here. Alright, so I just cleared everything. So we know that our velocity is 4.47 meters per second as the bullet block leaves. So we know that before we had some bullet, that does not look like a bullet, whatever. So we had some bullet speeding and some block not moving. Then later we have some bullet inside a block moving together, and our velocity here is 4.47 meters per second. Alright, we know the mass of both the bullet and the block, so we can figure out this mass. It's just whatever the mass of our block is, plus the mass of the bullet. And before we know, so we know that momentum, again, we already said before that both our quantities must be the same. So we have a very good idea that these two things, conservation momentum, no matter the collision, momentum is still conserved as long as I consider everything in my system, which it's a bullet block system, everything is in there. So we know that whatever our mass of our bullet, which we do have, we can now find, if we know these three things, we can find this fourth, whatever our velocity of our bullet is originally. So I'm going to set that up more as an equation. So we know that my initial momentum is equal to my final momentum, or at least the sum of my final momentum. And then we know that my momentum here is equal to the total mass, so that's mass of my block plus mass of my bullet, times the velocity of both. I'm just going to put velocity, and then that my original is equal to the mass of the bullet times the velocity of the bullet. And remember, we're solving for the velocity of the bullet. I'm going to write in red up here just so we can leave that up, but use some more space. So therefore, if these two things are equal, that means these things are also equal to each other. So we can say that mass of our bullet is equal to velocity of our bullet, or times velocity of our bullet is equal to mass of the block plus mass of the bullet times the velocity of both. And we're solving for this one. It's a terrible color to pick. We're solving for this one. So if we divide on both sides by this b, we'll now have a final equation of VB equals mass of both times the velocity of both divided by the mass of just our bullet. And then from there we can plug in all those things, because we know this velocity, we know these masses. You could go from grams to kilograms. You absolutely don't have to. It is an option. So I'm just going to plug in those numbers really quick. Alright, so I plugged in all my numbers. 250 for the mass of my block, 8 for the mass of my bullet, 4.47 for the velocity of both divided by the mass of just the bullet, and I got 144 meters per second. So this makes sense. Honestly, in my opinion, it looks a little slow, but it could just be a very large bullet. Say if you're shooting like those bean bags, those go fast, they don't go that fast. But it should be a very high velocity because it's a bullet. Alright, so hopefully that helped you on this page. We're about to move on to the next one. So this will be deleted, so pause if you still need it. Alright, so I was already talking about the reasonability, because anytime you do something, you should ask, is it reasonable? Because most of these are based on real life. In this case, it is relatively reasonable. It probably is a, thicker, heavier, not to say heavier, it's only 8 grams, but definitely maybe not as good at reducing air resistance. But, it is a reasonable answer that your bullet is in the hundreds of meters per second. So the next one is now, well, we know what happened if the bullet was that size going that speed, but what if it was moving at the same initial speed? If you need that number, we got about 144 again, meters per second. So, but we double our mass. So instead of just m, it's going to be 2m. And so how far will the block land from the table? So something you think about is now how much more momentum is going to get transferred, and how is that going to transfer to more velocity? So you could recalculate this, but you'll notice they're not giving very exact answers. So if you look back at the next problem, or the previous problem, it says that it should go 2 meters before. So now we have twice as much momentum. So is it going to go less or more? Because that'll just cancel out or the same. So just looking at it, if it's going to be have twice as much momentum, you can probably imagine it's not going to go less distance, right? If you're hitting something harder, right, more mass, it's definitely going to go more. So that kind of cancels out all these really tiny ones. So you know it's going to go more. So the idea is it going to go more but not twice as much, exactly twice as much, or even more than twice as much? So we can look at this a couple of ways, but the one thing to think about is, so we did double our mass, right? So we doubled our total momentum. So I'm just going to write 2mv is now equal to whatever our 2m plus our big block. Remember, this is from the bullet. So is this. This is the block. And then times some velocity. So this velocity is definitely going to go up. And it would be twice as much if we did not have this in here. So since that's in there, we are also increasing the amount of mass this thing has to use. So if we're increasing that a little bit, we are decreasing this a little bit, even though we just said, oh god, we got to increase that by twice as much. If I'm not explaining this well, I'm sorry. It sounded better in my head. But the main idea is, yes, velocity will definitely increase, but not exactly by twice as much, because we are also increasing here the amount of mass it needs to move. So we are increasing the velocity, but just not twice as much. So if we are increasing it, we're also going to be increasing the distance by as much, but just not twice as much. So the most correct answer in this case is more, but not as much. And the key factor here was that we increased the mass on both sides of this equation. If we only increased it on one, but this mass was kept constant, then the velocity would have to be double, and since the velocity is double, it will go double distance. Hopefully this was helpful and not confusing, and I will see you guys in class.